Hey, hello again. We are taking a look at section 6.5, which is dealing with, I don't know how to integrate it. The table doesn't have it either, the table of integrals. So what do I do? Well, you can chop it up and do Riemann sums in peculiar ways to come up with an approximation of your integral. So the three methods that we are studying are the midpoint, which is actually from Calc 1, where you had left endpoint, Riemann sum, right endpoint, and then midpoint. Sometimes teachers teach it as well. But then we ran into something new called the trapezoid method, and finally Simpson's method, which is based upon actually connecting 3 points on the curve and forming a parabola and calculating the area under the parabola versus underneath the curve itself. These are rather rudimentary. They're pretty good. To start with. You got to start somewhere. They have a lot of math into this where they've gone into what's the error on Simpson's, and it's based upon, other things. But we don't do that. We just want to learn how to do it. And we're going to use a calculator, okay, to do the problem. So the problem is in front of you, and let's look at an example. Where these formulas came from, I can discuss a tiny bit because this video is also going out to another class that maybe I didn't discuss it with them. So we have to maybe look at that. So this could be lengthy, except I've already computed the numbers. It's just tedious to write out the sums. Anyway, use approximation techniques, midpoint trapezoid, and Simpson's methods to approximate this integral that I gave us. So it's this guy right here. And also they need to tell you how many subintervals. And as you're learning, the more subintervals you chop it up into, the more calculations you have, but the better the approximation typically on these continuous functions that we are considering. So the first thing you want to do is take the interval, what interval, and break it up into n pieces. The interval is just look at the problem itself and you see, oh, we're integrating from 4 to 6. So the interval they're talking about is from 4 to 6. So let's take a look at that guy. Pretend you're on a number line and we're going from 4 out to 6. And you guys divvied up as best you can into 10 equal subintervals, okay? The fastest way, I think, is to use the formula b minus a divided by n, which is take the upper point of the subinterval, which is in this case 6, subtract from it the lower limit, which is 4. So the width of the subinterval, the interval you're integrating, is 2. And you're going to split it up into, in this case, n pieces. Okay, so it ends up being 2 over 10 or 0.2. So that's our b minus a over n. And what that's really doing is just basically telling you how wide each subinterval is. So this is 4, but then this is 4.2, right? And then 4.4, 4.6, 4.8, here's 5, here's 5.4, for example, and on down the line. And those guys you're going to want to know because in the trapezoid and the Simpson's rule, you're going to be plugging all those numbers into the function. What function? Oh, the function we're integrating. That's also important to see. The natural log of x cubed plus 2, which, how do you integrate that? I don't know, but what we're going to do is approximate it, right? Okay, so the first one we'll mess around with is midpoint. As soon as you got all those numbers, you got 4, 4.2, 4.4, here comes midpoint, and midpoint says, no, I don't want those numbers. What I want are the midpoints of those intervals all the way down the line and figure them all out. And there's 10 of them because there's 10 subintervals. So between 4 and 4.2 is 4.1. Between 4.2 and 4.4 is 4.3, and then you see the pattern. It's 4, 5, 7, 9, 5, 1, 3, 5, 7, 9, and that's it. Okay. Okay, so a little bit about the midpoint method. So you have a curve here, and you want to approximate the integral over, say, let's pretend that we're at 4, and this is like 4.2, the very first subinterval in our problem, okay? So what happens is we take an arbitrary number like we do in Calc 1. We take an arbitrary, in this case, we're going to choose, why don't we choose the midpoints? And so we'll go 4.1, okay? The function up here is the natural log of x cubed plus 2, whatever it looks like, we don't know. But what we're going to do is we're going to calculate the area of the rectangle whose width is from 4 to 4.2 and whose height is calculated by plugging in 4.1 into the function. So 4.1 cubes plus 2, take the natural log of it. That'll tell you how high it is, and the width is this much. Well, each one of these subintervals is multiplied by that same width. That's why the formula says up here for midpoint, this is just the width of each subinterval, and then what you see in here are all the heights. So the way you do midpoint is you plug the numbers, the midpoints into the function and add that all up. So the way this starts for a midpoint, and I'm trying to make this quick, right, is it's equal to b minus a over n, which we figured out to be 0.2, and then inside you just take the function of every midpoint. So the first one we found over here is 4.2, okay? So we're gonna plug that in, we're gonna go natural log of 4.1 is the midpoint, 4.1 cubed plus 2, like I just did in the picture. And then you're going to go to the next midpoint, which is natural log, and you can use your number line up here to help you figure it out. It looks like it's 4.3 cubed plus 2 plus, you know what? Plus, there are 10 of these, okay? And I'm just going to cut to the chase and go all the way out to, say, the last two to show you. So we have the natural log of, say, 5.7 cubed plus 2, and then finally plus the natural log of 5.9 cubed plus 2. And that's your computation. How you do it is up to you. Me, what I do is I first, on this guy, I go 0 equals, and then I do this really cool thing. I just go plus, and it says answer plus. Okay, if you know what I'm talking about with these guys, they're really cool. And then you type in the formula once, and you hit equal, and then you go plus, and then it goes answer plus. And then you change the numbers. So the first numbers I'm going to put in are going to be, let's see, look down here. It's first numbers I'm going to put in is going to be 4.1. Then I go plus, and there it is again, and I change it to 4. All I do is change the 3. And then I change it to 5 and 7 and 9. And then I get into the 5. And so I compute it rather rapidly that way. And for this guy, what I got as an answer is the following. So let's see if I got this somewhere. 9.65059, 9.65059, and then I think it's 12306. I recommend that you write out all the numbers that you see in your problem and say, there you go, that's my midpoint approximation of the answer, okay? At this point, you might get curious to know, what is the actual answer? I don't know how to integrate that, but what I did do, I did us all a favor, and I went online. I think on this one I used Wolfram Alpha or whatever, and I got this answer. I got 9.65053, and it stopped. 9.65053, and that should be enough. That's a 6, okay. And then you can compare, and we're pretty good. Midpoint's very good approximation of the actual with just 10 subintervals. That's pretty good. Goes all the way out to 4 decimal places before it diverges, or maybe 3, okay, if you round. All right, so now let's do the other two, and I'm going to go kind of quickly on these guys. We're going to talk about the trapezoid method next. And the trapezoid, basically, it's similar. If you're going to do it without thinking about it, it goes like this, 0.2, but then there's a 2 under there, which we can explain in a moment. And then it's really strange. You start at the very left endpoint, which in our problem is 4, and you call that x0, okay? So you're going to use the left endpoint and all the middle endpoints and then the right endpoint. And it turns out there's actually, in this case, 11 terms instead of 10, because there are 10 subintervals, but you got the 2 outer guys, and so you counted an extra number. Looks like this. So it would be the natural log of 4 cubed plus 3. Now, the weird thing about trap is this. Then all the guys inside have a multiplier of 2, okay? Then you have natural log of 4.2 cubed plus, and I said plus 3, it should be 2. That's the kind of stuff you happens to me. It makes me crazy. Plus, so you think I'm goofy or something or whatever, but I didn't used to do that. Plus, and then you go all the way plus dot, 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 plus. Let's do the last two to show you. It's the natural log of, what would it be? 5.8 cubed. I forgot somebody. Who'd I forget? A 2 in front. They all have 2's in front, and then plus 2 in here. That's the formula. And the very last one, only 1. So it's the natural log of 6 cubed plus 2, and that's your calculation. Now, the reason it looks funky is because with trapezoid, if you're connecting these guys, say you're at 4 and then you're at 4.2, right? The trapezoid method, what it does is it goes up here and makes this line here, which is really natural log of 4.2 cubed plus 2. And this line over here, which is natural log of 4 cubed plus 2. And they connect these guys with a straight line and create, guess what? A trapezoid. Okay? The area of the trapezoid. Now, the height here is 0.2, which is our b minus a over n. But the funny thing that happens is the area of a trapezoid is 1/2, and then there's a height, and then it's the average. Then you have the b1 plus the b2. Well, the b1 and the b2 are actually the sides, okay? And the height of this thing, it's sideways, is the 0.2. Okay, think of it that way. You can pause and think about your geometry, but notice the 1/2 there. And notice also when you go to the next trapezoid, you use this side twice. So that's why, in a nutshell, you got a 2 out here with the b minus a over 2n is the formula. And then you got all these 2's in the middle. Okay, so for this one, the answer I got, let's put it in the same color here. The answer I got here for trapezoid computing all of that was, where are you? 9.64975. 9.64975. It's not 6. 9.64975. 3180. 3180. And here you can start making comparisons. Which number is closer to the actual answer? Right now, I think midpoint is doing better than trapezoid. Trapezoid's close, but a little bit off. The last one I don't explain in class. I just simply go, when they do Simpson's rule, what they do is you've got the curve doing its thing. You got, okay, this is 4. Over here, this is like 4.4. And here, this is 4.2. And in a nutshell, the idea is, let's grab these 3 points and fit, as we do in pre-calculus or other classes or algebra 2. Let's find the ABC that creates a parabola. Y is equal to ax squared plus bx plus c. So we take those points and we plug in and we solve the system when we get the a and the b and the c in the equation. And then you integrate a parabola, which is easy for us, and we can't do the original function. Anyway, you get the drift. I don't typically do the algebra. The only thing for you guys to know is this becomes 0.2, which is b minus a over n, and then there's a 3 multiplier. And inside here, it's still natural. The trapezoid and Simpsons are very similar. You've got, let's see, 4 cubed plus 2. But then it's, instead of going 2, 2, 2, 2, 2, instead it alternates. It goes 4, 2, 4, 2, 4. And the first one's a 1. Then it's the left endpoint. Then you go 4 natural log of 4.2 cubed plus 2 plus, I'll do another one, 2 natural log of 4.4 cubed plus 2 plus, and now in the interior, you're just going 4, 2, 4, 2, 4, 2, 4, 2, until at the very end, it's just 1 natural log of 6 cubed plus 2, and that's it. That's a 6 right there, okay? You can't see it. There you go. So that's what you do. And when I computed this last one by hand, we got a 9.6505, 9.6505, 25584, 25584 for me. And it keeps going, of course. All of these keep going. And when you round off, it's not exactly the answer. But these are the three. Now, you know, it's interesting what you can do is you can do stuff, well, let's take Wolfram, which is up here, and subtract, you know, these guys to find the magnitude of the difference between these numbers. And you can do a very quick comparison on it. So we do things like that. We go, well, how far apart are each of our estimates? Which one's the closest? Well, it would have the smallest difference when you took when you subtracted. Now, if you subtract, it could be positive, could be negative. What we do in math is we put absolute value, and that's how we measure error. I don't care positive, negative, just compute it and make it positive, and you'll find the difference. Another thing you can do is you can take that difference and divide it by the actual number, and it'll tell you the percentage error that you have in your problem. So you could be working on something, the answer is really small, and your error is smaller than it, but compared to the answer, it could be a rather large percentage that might be not what you want. So there's stuff here that is fun to do and to take a look and see which technique is the best. This is just an overarching, here's how you run through the thing. You can pause and look at it anytime you want. Thanks for watching. We'll go on to some other stuff as soon as I can stop this recording.